Okay, welcome to part 2 of matter and the periodic table. Let's start with the periodic table of the elements. Remember that columns are known as families or groups. So if I look up and down a periodic table, like in this column, for example, right there, that's known as a family or group. Beryllium, magnesium, calcium are all in the family or in the same family or group. If I look across the periodic table from left to right, rows are known as periods. Rows are known as periods. You should know where the alkaline metals, alkaline earth metals, transition metals, halogens, noble gases, and intertransition metals are on a periodic table. Let's start with the alkaline metals. The alkaline metals are this first column right here. They include things like lithium, sodium, potassium, rubidium. Everything in this first column is an alkaline metal. Alkaline earth metals, second column. Alkaline earth metals include beryllium, magnesium, calcium, strontium, and so forth. Second column is known as alkaline earth metals. Transition metals are this large group. The majority of the periodic table, in fact, are the transition metals. They're this group right here, not including the first two columns, but this group right in here are the transition metals. The halogens are the second to the last group. Fluorine, chlorine, bromine, and so forth are the halogens. Move over one for the noble gases. These are the noble gases. And the intertransition metals are down on the very bottom. These are the intertransition metals. They fit into that slot right there. And so you should know where these are on the periodic table. I want you to take note of this zigzag line right here. Along this, where I'm drawing right here, where I'm outlining right here, that zigzag line is the line of demarcation between the metals on the left side of the periodic table and the non-metals on the right-hand side of the periodic table. These metals themselves are known as semi-metals or metalloids. But everything to the left is a non-metal, everything to the left is a metal, everything to the right is a non-metal. Let's take a look at some trends in the periodic table. The periodic table lists elements in order of increasing atomic number. As I look from left to right, top to bottom, as I read this way, hydrogen, helium, lithium, beryllium, and so forth, I notice that atomic number goes up. Now, what's atomic number? It's the number of protons in the nucleus. As I go from top to bottom, left to right, top to bottom, like I would read a book, atomic number increases. That'll become important later. Atoms with the greatest ionization energy and electron affinity are in the upper right-hand corner. So ionization energy is the energy required to remove an electron. The energy required to remove an electron from an atom. Electron affinity is very closely related. It's the power with which an atom pulls electrons towards itself. So electron affinity and ionization energy are highest in the upper right-hand corner of the periodic table. Highest in the upper right-hand corner of the periodic table. Notice that's just the opposite as atomic radius, and I'll talk about that in just a minute. But the point is that upper right-hand corner of the periodic table is important because that's where the elements with the highest electronegativity and ionization energy, electron affinity and ionization energy are. Things like oxygen and fluorine. All those elements in the upper right-hand corner have a high electron affinity and high ionization energy. They also have high nonmetallic character. So as I move up, lower left to upper right, nonmetallic character in the upper right-hand corner, metallic character in the lower left-hand corner. Electronegativity, very closely related to these two, very closely related to electron affinity and ionization energy. Electronegativity also increases as I move from left to right, lower left to upper right on the periodic table. Electronegativity, the power with which an atom pulls electrons towards itself, electronegativity highest in this upper right-hand region of the periodic table. We've talked a little bit about size. Atoms get smaller as you move across a period, and they get larger as you move down a family or group. Let's talk about the size across a period. As you move left to right across a period, atoms get smaller. Now that's really kind of counterintuitive because we've already said that atomic number gets bigger and bigger and bigger as you go left to right. So if you have more and more and more protons and you have more and more and more electrons, wouldn't that stand to reason that atomic radius size would get bigger? It doesn't. And the reason is because of something called a nuclear charge. As I move from left to right across the periodic table, the positive charge from the nucleus and the negative charges from the periphery of the atom, from the electrons in the outer reaches of the atom, attract one another. And in doing so, the atom gets smaller and smaller and smaller. Think of a tug of war between two teams. As you add players to each side of the tug of war, the rope between them, the length of the rope between them gets smaller and smaller and smaller because they're tugging on each other with greater force. The same thing is true here. As I add electrons in the same main energy level, I'm adding electrons in the same energy level because those electrons are all going in on the same main energy level if they're on the same row. Then what's happening is that I'm getting a greater nuclear charge, and these subsequent electrons that are being added are not undergoing a shielding effect from interior electrons. The electrons are going in on the same main energy level, so they're not shielding internal electrons, as opposed to going top to bottom. As I move from top to bottom, what's happening is electrons are being added to subsequently higher main energy levels. Therefore, the electrons that preceded them will shield them from the nuclear charge. They will partially shield them from the nuclear charge, allowing the atom to get larger and larger and larger as they move down a column. Down a family or a group. The point to remember is moving left to right, atoms get smaller. Moving top to bottom, atoms get larger. All elements in the same family or group behave similarly because they have the same number of valence electrons. If I isolate any family or group, let's take this one for example, everything in this column is probably going to have the same physical and chemical characteristics. It doesn't matter what column I choose, they're all going to be the same. If I look at this column right here, they're going to have a tendency to be similar physical and chemical characteristics because they are in the same column and have the same number of outer level or outer shell, or what we call valence electrons. For example, the first column of elements are known as the alkaline metals. Because they have one valence electron in their outer shell, they behave similarly. Alkaline metals react violently in the presence of water. If I look at this first column right here, they all have one valence electron, all behave the same similarly, are explosive in the presence of water. If I looked at the noble gases on the right-hand side, they have a full octet of electrons in their outer shell and therefore are relatively unreactive with other elements. So if I look at to the opposite side of the periodic table, if I look at helium, neon, argon, krypton, and so forth, these are going to have a tendency not to be reactive with anything else because they have an octet of electrons in their outer shell. They don't want to react with anything else. They all behave the same because they all have the same number of valence electrons in their outer shell. The ions formed from the alkaline metals and the alkaline earth metals are smaller than the atoms from which they are derived. They are positively charged because of the loss of electrons. We're talking now about ion formation. If we look at a periodic table, we see that atoms on this side of the periodic table are going to tend to lose electrons to be like the preceding noble gas. For example, lithium will lose one electron to be like helium, the preceding noble gas. Sodium will lose one to be like neon, the preceding noble gas. Magnesium might lose two. Magnesium has two valence electrons and would like to jettison those two in order to be like the preceding noble gas and have the octet of electrons in its outer shell like neon. And so elements on the left-hand side will lose electrons and in doing so become smaller. Elements on the right-hand side, just the opposite. Fluorine will gain one to be like neon. Oxygen will gain two to be like neon. Isoelectronic, not the same as neon, but at least have the same electron configuration as neon. This is because cations are formed by losing electrons to obtain an octet of electrons. When they lose these electrons, they become smaller. Anions, on the other hand, become larger because they gain electrons to obtain an octet of electrons. I will see you on the next video podcast. Thank you.